I would like to dig into the nitty-gritty. I'd like to actually talk a little bit more about problem definition and deconstruction with Bob Lee. Bob is from the Open Innovation Project Lab at Wright Brothers Institute. You're going to hear more about their work with the Air Force Research Laboratory and the very strategic approach they use to digging into problem definition. So Bob, come join us.
Thanks, I'm very excited to be here. I do want to tell you that we're actually very new at this process. We really only have been working on award challenges, I think, for about a year over at the Idea Lab. I work with the Wright Brothers Institute. We're a nonprofit organization, if you could switch to the next slide, please, that works under a partnership intermediary agreement with the Air Force Research Laboratory. One of the reasons why the Air Force Research Laboratory wanted to get the Wright brothers involved with this is because everybody in an organization and an agency is always too busy doing their current job, just try to figure out how to do something new and something innovative. Okay, so they wanted us to become the people that come up the learning curve so that we can make the entry easy for the operators that are coming in. So if you think about every process that you deal with, there's a learning curve. Getting an expert into the area who understands the law, the legal parts of this. What do you really want? All of that planning that Kristen was talking about, those are the things that we try to do at the Wright Brothers Institute. We try to experiment by running through real problems with people. Next slide, please. In the Idea Lab, we actually have a, take the first build on that. We talk about things being in the problem space and the solution space. In the problem space, one of the problems that we have with people in their problems is that we are trained all of our life to go into the solution space. So we tend to go after the very first solution that we come up with. So we try to think and we're there. So what we do is we continually put people back in the problem space. The next part of the build, please. And we do that by making people diverge. Kristen mentioned about in the front part, if you can get very divergent people into there, you get more creativity into that problem space. What is the real problem that you're trying to solve? Why is it that you couldn't solve it? We've actually brought in artists and engineers together, and that's been a very real interesting mix about trying to get people to think about their problems in different ways. The yellow things that are up here show you different types of tools that we use, and I'm going to talk about a couple of them in a little bit. But that divergent collaboration of getting a lot of different type of people in thinking about it, because if the same people could solve the problem, it would have been solved. So you need different minds, different thoughts, different capabilities into it. But you can't stay in the problem space forever, so eventually you have to reconverge onto something, if you give me the next build, to something what we would call, oh, there we go, thanks, a redefined problem. Once you get to that redefined problem, then you can start working into the problems, or the, oh, that's the backwards one. Let's see, this one. This one? Alrighty, this one. This one. There we go. Got to figure it out. Technology. You get to the redefined problem. Only then can you then decide whether you want to take that internal to your organization or out to the world. I've been basically was hired to help bring that part that brings it out to the world to get that award challenges out to even a wider idea. Before we get started with building an award challenge, one of the things we've learned over the years is you're in the award challenges, you're really focusing on the ideation part of transformative innovation. But really there's many parts of it. There's three parts that ultimately are going to transform the world. You can get a great idea, and then we ultimately have to work that into the engineering parameters. As we talked about the vehicle stopper problem that we put out there, we got a great idea, but now we actually have a team that's working on the engineering part of that to actually take that into completion. Another thing that's really interesting about getting new ideas from the world is sometimes organizations aren't ready for those solutions. So we had a hard time going from the first part to, hey, who's going to now take the next step? Because we didn't think that there was a solution, so we didn't really plan for that. So we now had to stumble through the first part. So what Kristen mentioned about thinking about what you want to do with this result when you're done, that's a very important part of that planning process. And then figuring out, well, what kind of user buy-in do we got to get? what do we need from the ultimate end user who's going to use this, and get them involved in the process up early. When I first came on board, I thought that I was hired to handle this middle part, that real small thing. What we've learned is that I have to help people from the preparation end all the way to the after action end. So thinking about the project as just awarding a prize, you really need to think about the fact that that's where the work is. There's not a lot of work in the middle part of this process, but there is a lot in the beginning and the end. And this is kind of the way that we break down that first part, which is what I was asked to talk about in the area of building the problem. So what we do and what I do in the Idea Lab is that we take a person that comes to us with a problem, and I literally help them through every step of the process. That lowers the barrier for entry. These are some of the problems that we see out there. And very early in my career, I had a boss that told me, he said, think about being wildly successful. In an award challenge, that's what you got to do. If you're wildly successful, who would get excited? If you're not going to get excited about the result, then don't start. Okay? If your solution to this problem that you're trying to solve draws a yawn, tell the guy to go away. Let's get a real problem out there. Then we got to think about, one of the things is, how much effort have you guys been working on to solve this problem? What things have you tried in the past? We don't want our solvers out there to actually solve a problem that we've already seen the problem, been down this path and we hit a block. So show them not only where you hit the block, but why you hit that block. If you can put that out in the problem statement of the challenge, you can get much better solutions coming out of the end. This is about problem deconstruction. If you start out with a thing where you say, I want to design the UAV of the future, that's too much like world hunger, you know? We need to figure out, what is it, the particular part? There may be particular parts of that problem, so we start breaking it down. Where is it that causes me to not build that thing in the future? Is it really safety? Are you talking efficiency? You know, once we get it down to there, then you can basically go into the specific problems that would ultimately help to make an improvement into that thing. This is what I call identifying the technological long pole in the tent. If you can find the piece that you need to solve, then that's the area that you want to concentrate your prize on. Let's give you an example of problem reframing. The folks from the RZ Directorate, the Propulsion Directorate, basically had this problem with volcanic ash, and they said to me, we need a better model for volcanic ash dispersion because we want to be able to fly around it, and that costs us a lot of money to fly our planes around where the volcanic ash is. As we began to discuss the problem, I was asking a series of questions to the guys, and what we found out is that they don't have a modeling problem. There is a model out there called high split. What it doesn't do is it didn't have some of the very components that cause damage to the ash. So when we ask these questions, what causes the damage and how can we get good inputs? What we didn't we started to switch from a modeling problem to a gathering of input data. Good inputs to the model make good things. So I asked questions, why can't you get good inputs to the model? So we reframed that problem down to how do we get a sensing problem that would actually show me what kind of a dispersion we have? Comes to find out that the initial conditions on the volcanic eruption where nobody's out there and sensing is where a lot of the problems are. So if we could get better inputs right at the initial conditions, that would be where we want to start to solve the problem. We're still in the problem definition phase of this problem. Now this is an example of problem deconstruction, okay? And this is the a problem of a strain gauge in a high temperature jet engine, okay? We started in the green spot there of saying, well, what is your current problem? What is your current practice? The Fabry-Perot interferometer method is what they had. It uses a quartz material, and you see that 1600 degrees in the red. That's where the problem hit. So I said, okay, so the problem is that the quartz breaks down at that. Is there any other materials they can have? We actually did some look around and we found out that there was a sapphire material that you could have. It wasn't out in the literature, but we called the company and they'd actually done a test and was able to measure strain in a boiler in Hamilton, Ohio, right down the street from us, okay? So immediately we had a solution to this, but that solved half of the problem. That allowed me to do static measurements, but not a dynamic measurement inside of a jet engine, where we also have a lot of noise, some very 170-degree acoustic environment that's shaking the heck out of it. And the sapphire breaks down at that material. It's brittle. So we started asking questions, well, how else can we solve that problem? Are the two problems that you're solving, are they interdependent? If they're not interdependent, then basically you can separate the problem and now you have a solution. So if you take a look at the little light bulb there, that immediately came to mind, okay? Now we could have put out a prize and had something going on there, but we wanted to push this guy back up into the problem space and said, okay, that's how you do some kind of direct. How would you do other indirect methods? You know, because an interferometer method is an indirect type method. Are there other ones? Can we use capacitives? Immediately we started looking down there, and you could look at, what if we could have the points tell us where they are? Some kind of an RFID that would tell you where the points are, and then you start looking at it. That led to another idea. We went back up into this and said, what are more direct measurements? If we can have something tell you what it is, maybe we can use other spectrum, some other things that we can do. So immediately within, and again, this took about, I'd say 2 hours with the guy, and we were able to come up with 4 different ways. If you look where I guess it's over on the left-hand side of the chart, and you see the idea down there. When he started looking at all these possible ways of solving the problem, he really got excited about the one on the lower right, because what he realized was that if I can solve this problem, and it really looks actually very solvable, then I actually have a way of doing measurement strain in multi-dimensional things, so I could get a much more robust answer if I pursue that one. And this is one of the problems that we find. People tend to go after the first solution that they can think of and then hone in on that. By staying in the problem space, you can get a broader look at where those problem spaces are. Problem deconstruction. We use a lot of concept maps. Professor Novak from Cornell University has a book out on that to talk to you about it more in depth. But basically what you're doing is you're starting from the need, you're working through to a real life situation. This was a problem that we had with ultra high performance concrete, and we were looking at how do we stop a missile from destroying a building or a high value building. And then as we break that problem down into, like, say, the functional mechanisms that we want to look at, you'll start to notice that there were 2 functions that we were trying to look at. The functions were, how do you absorb the energy and how do you dissipate the energy? And now we were trying to ask one material to do both of those functions. Immediately that led us to an idea of, well, what if we didn't have that? Can we use it some other things? So what are the properties that causes something to really be able to absorb that energy? And that's why they're looking at high performance concrete, ultra high performance concrete. But they couldn't control some of the processes. So now we get down into the material processes of how does that concrete form and what causes those bonds to make that very, very solid. If we started boring in on that problem, we can start to see where we have a potential for a better solution to this problem. Then once we get to past that, one of the things I call is very important is that we do technology due diligence. Again, Kristen alluded to this earlier, but we had a guy come to us and ask us, hey, I want better petascale storage, okay? Now that's basically a solution, not necessarily a problem, so we ended up having to push him back into the problem. His current cost was about $1 to $2 million if you look out there for petascale storage. So we started looking around, and very quickly we found, I don't know why he didn't find it, but we have tools for really digging in and finding, searching worldwide patents, things that we can do outside of the base that they can't do inside of the base. We have access to a lot of other areas there. So we found this inexpensive backblaze system, so immediately we could build a RAID system, a triple redundancy system there that would allow you to get to, for about 1/3 the cost. But we didn't stop there. We reframed the problem, and what he really wanted was, I don't want just a system, I want something that's non-proprietary so I can exploit the nature of my data and start to actually look at it. So what we did was we found out that there's when we looked at it, we found there was an open source capability called Ceph, but we also found a research paper that was out there, and that allowed us to saying if you go to petascale storage, you can do something other than a RAID type storage system and basically do this with a double redundancy system and get higher reliability. So with all that information, he is now taking it back. He's hiring an intern. They're going to build the system and actually go ahead and put it on out there. We didn't even have to get to a word challenge by really working this problem first, by doing our technology due diligence. The third problem, okay, I got to move on real quick. There's a lot of opportunities of defining what type of challenges you can use. This is a Prodigy challenge when you really can define basically how you're going to score something. So it's kind of like a leaderboard where people compete. So you're taking that natural competitiveness of people and putting it out there. I do want to mention to you that this is an example of what we call this is the results of the first year that we have on the challenges out there. If you see the dashed lines, Kristen mentioned about getting other people out there. We went out and paid $3,000 to Popular Science, so we advertised up in Popular Science. They created a direct link to challenge.gov, and we really upped the number of people that seen the challenge and responded to it. Am I running out of time?
I think we should.
Okay. I was going to show you, nobody likes talking about the prep part, everybody likes talking about the results part. So I'm going to go ahead and just spend a couple minutes just talking about this. This is a problem it's a fast rope challenge. Okay, the fast rope challenge is where special operators will jump on a rope, they'll come in very quickly, many times under fire or potentially under fire. They jump on the rope, you get lots of men coming sliding down the rope, and it can build up a tremendous amount of heat on the hands. Our special operators, when they've come down, actually have had blisters on their hands from the rope. Many times we've had people falling off the rope. In this case here, the video is going to show an example of a person that actually fell from this rope. He got slightly injured. It jammed his back. If he'd have been up at the 90-foot, he would have actually caused a real problem with him. This gives you an idea of where we've gotten our solutions from. We had 1,300 project rooms from 69 countries, 182 submissions. Here's the punchline on this. Within 3 months, we actually come up with material type solutions and a mechanical type solution. Within 5 months, we actually went from an operator coming into us with a problem to actually having working prototypes in this thing by being able to post this. The way that we did that was we got the material solution people excited about this. The solution, we went out and called some glove manufacturers. The glove manufacturers actually said, we didn't know about this material. They went and put the prototypes together for us for free. We had 7 different prototypes that we built. We got them all in there for free. We then actually tested them in some things. Total cost today, $26,000, a tenth of a man-year of effort, and we went from problem to prototype in 5 months. Here's my get off the stage slide. By really prepping it, solved prior to posting, we got a large percentage of our problems are solved. We've actually had challenges withdrawn because people couldn't get excited about the results. We've actually had 5 challenges that were awarded. We have 2 more that are out there, and we're going to be posting some more. So we should have some more good stories for you. Okay, thanks.
So I found that really interesting, and so I have one opening question for Bob, and then if any of you have a follow-up question or two, please come to the microphones in the center of the room and we'll make sure to get those to Bob. My question for you is that you did a really great job of explaining how to break down these intense engineering, complicated challenges where you were looking not just at how to chunk out and break out the problems within a complex technical problem, but also how to look around the landscape beyond that problem to see where you might get some helpful tools. For the folks in the audience who are not working in an engineering landscape and in a science and technology landscape, do you think that this approach to problem definition is equally applicable?
This is one of the places where you need to get that broad area of people of expertise into the group to just really discuss the problem space. Because as you begin to push back up into the problem space, you can do this with facilitators, and typically the guy that's coming with the problem is the technical expert, But what he doesn't do is needs somebody to keep pushing him back up into that space and actually coming at that problem from a lot of different directions. So the more diversity of group you can bring into there, the better your solution, better your look at the problem space are going to be.
That's fantastic. I think that points back to our encouragement of you to bring in outside thinkers. Any questions for Bob at this point? Okay.